Hey everyone, welcome back to yet another Euphoria Academia past paper YouTube video. Today we're going to be doing the grade 12 physical sciences paper 1 that was written in November 2023. We're going to be covering electric circuits and all the questions that encompass electric circuits. My name is Ole and I'll be taking you through it. So without further ado, let us get into it. Alright, starting off with what we see in multiple choice, question 1.8, we have 4 voltmeters, V1, V2, V3, and V4, and they are connected in the circuit as shown below in the diagram. So the question asks which voltmeter will have the same reading as voltmeter V1 when the switch is open. So here in the voltmeter V1, this is essentially measuring the voltage across the whole circuit. All right, so it will measure the potential difference if you follow conventional current, which is the current flows from the positive terminal of the battery. So it will flow in this direction all around the circuit, and then it will come back to the negative terminal of the battery. So this V1 measures the voltage change or the potential difference across the whole circuit. All right, so there will be a difference here. Here we'll probably have like a higher potential, and here we'll have a lower potential, probably the lowest. So that V1 is measuring the difference between these voltages. All right, cool. Now, if you look at it, this V4 will actually measure the potential drop here. Right, so it will measure this one, the high one coming from the battery side, and then the potential drop across this ammeter. All right, so it will not have the same reading as this guy over here. All right, and then V3, well, V3 something is happening, right? So it's measuring the potential across this whole circuit and then measuring it against this circuit. So when switch S is open, we are not going to have any current moving throughout this circuit. So that would mean that the current that flows from the battery and then comes to this side of the switch is actually the same as the potential difference from V1, and then because there's no current flowing, that potential difference will be mapped to here. So V3 only is the only one that's measuring the same as V1. It was a bit long-winded. Let us get into the meat of the question. The main question of that we want to get through, that is electric circuits, is question 8. All right, so it starts from 8.1 and then ends at 8.3.2, and it has a total of 18 marks. Let us go through the information. So question 8 states that the circuit diagram below shows a battery with an EMF of 12 volts and internal resistance of 0.5 ohms, and that is connected to 3 resistors, a light bulb, a switch, an ammeter, and connecting wires. The ammeter and connecting wires will have no resistance. Okay, let's quickly check out what's exactly happening in this circuit. So following conventional flow, the current will flow from the positive terminal of the battery. So maybe let's call that I1. And this I1 will actually be, because we have a parallel circuit, this I1 will actually be the total current flowing throughout this circuit. So I1 will flow through this ammeter, flow down here, and then it will split into these two branches. All right, that current will split. So maybe let us not call that I1 but I total. So in this circuit we will have a current of I1, and then here we're going to have a current of I2. So this current is also going to flow through here, through this light bulb, and then it's going to split up again in this parallel circuit. So we're going to end up having an I3 and an I4, and this current is just going to flow through the, if the switch is closed, flow through the closed switch, and then it will all connect again, and that will be our I total. All right, now the potential difference across this whole circuit is essentially going to be the same for the two main branches here, but because we have another branch set which is going to be R1 and R2, we're going to have a different potential difference. So there's going to be a potential drop here, there's going to be another potential drop here, a potential drop there, but essentially the potential difference across R3 and this light bulb, that will be the same potential difference. Right, maybe we'll call that VP1, and then here we're going to have the same potential difference, and we'll just call that VP2. All right. With understanding what's happening in this circuit, I think we can get a move on. So I just renamed everything though. So the total external resistance is 7.5 ohms as we obtained in the previous question. And then our RP12, which is the resistance across this parallel circuit, is 5 ohms. So that's just what I changed. Now question 8.2.2 is asking us to find the reading on the ammeter. As established before, we know that that is the total current that is going throughout the circuit. All right, so we're just going to use our equation for our EMF because we have everything except the total current. So our epsilon is equal to I, that is multiplied to our external resistance plus the internal resistance. Now we are told that our epsilon is 12 volts and we don't know our current. Our external resistance is 7.5 ohms and our internal resistance was given as 0.5 ohms. And when you do the mathematics, you're going to find that our total current across this whole circuit is equal to 1.5 amps. Question 8.2.3 is asking us to find the power dissipated by the resistor R3. All right. So just a warning, our total V external, so our potential difference across the whole circuit, not including the battery's own internal circuit, is not equal to the EMF of the battery. So it's not equal to the 12 volts. So we can't go and say that um, our power is going to be equal to V squared over R and use that V squared as the EMF, because essentially what's happening with the EMF, it's the total amount of energy the battery can produce, but it also has a resistance in itself, as well as there might be resistance in the circuit that we didn't account for, so it's not going to deliver the full 12, right? So we still have to find what our V external is. All right, now finding our V external, we're just going to use our relationship of Ohm's law, which states that the voltage is directly proportional to the current, blah, 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 blah. So we're going to say that is equal to that. Our V external is equal to our total current across the whole circuit multiplied to the external resistance. All right, so we already know our current as 1.5 amps and our external resistance as 7.5 ohms, and we multiply those together, we're going to get a V external of 11.25 volts. And now that we have that, we can calculate our power through resistor 3, as because the voltage is going to be the same across the whole parallel circuit, so the voltage is going to be the same here, it's going to be the same in entering here. All right, so let me just indicate that on the diagram. So our V external is the same in that branch, it's the same in that branch. All right, it's gonna change here. We're gonna have a different V here, diff V. All right, cool. Let us go back to answering the question. So our V external squared over the resistance of resistor 3, and that is going to, when we substitute, we're going to say 11.25 squared over our R3, which is 15 ohms, and that is going to give us a power rating of 8.44 watts. Question 8.3.1 states that if the resistance of the light bulb remains constant, how will the brightness of the light bulb be affected if switch S is opened? So if switch S is opened, we're going to have a situation where it's like that, and we won't have current flowing through that R3, but all of the current will be flowing through this branch right there. So that's going to be taking all of the current. There's not going to be a split in current. So what will happen? Well, the thing that will happen is that the brightness of the light bulb will increase. And I will be explaining that in the next question, which is the next question. All right. Okay, so I already said that the brightness will increase. And it's a situation because all the current will flow through that branch of the circuit, because switch S is open, so that means that there isn't current flowing through that branch. There is no current moving there, but all the current is moving through this branch over there. All right, so that actually means that the power dissipated by our light bulb will actually increase. All right, and we see that in this formula that power is equal to I squared multiplied to R. So we already stated that all the current, so essentially the current will go up. So the current goes up through the light bulb, right? And then the resistance is constant, so that doesn't change, stays the same. So that would mean that the power dissipated has to increase, right? And how much more is this current, right? So we're still going to use that our EMF, we know it. So our epsilon is equal to I multiplied to all the resistors, and our EMF is still 12 volts. We don't know our I as of yet, and our resistance is now, the external resistance is now 15 compared to the 7.5 that we had, and that is still 0.5. So that's going to give us a new I of 0.7 amps. All right, so before, this I was actually split, so we found that our I that went into the two parallel circuits, because we essentially had the same resistance, right? This was 5 ohms. So we had 15 ohms in the first branch. We had a total resistance of 15 ohms, and our total current was 1.5. So you divide that by 2. So we had a current of 0.75 going there, a current of 0.75 going there. But now the current going through this whole circuit is not 0.75, but is 0.77, which is higher than the previous 0.75 amps. Right? So the brightness will increase because of those reasons. All right, let's quickly do an RMS circuit. So it's still in the realm of circuits, really. And it's just that instead of now just doing DC, we're going to be doing AC. All right, so let us understand exactly what is going on here. So the circuit diagram below shows an electric kettle and toaster connected to the AC source, and they are in parallel to each other, and the RMS voltage is 220 volts. The ammeter, connecting wires, and the switches have no resistance. Okay, so the question 9.2.1 is asking for the definition, right? So just get your keywords right, and essentially what you need to know that the RMS value of the AC current is essentially the same current value that we would have if we're using a DC source. All right, so RMS, same as DC current or voltage. It matters on it just matters on if they're asking about the current or if they're asking about the voltage. All right, cool. So let's understand what's happening in the circuit. So it moves from the AC source, the current moves from the AC source, then is going to be split up into the kettle, and then the other one is going to go through the toaster. All right, and yeah, I mean, it's not really that complicated compared to what we had before. So the voltage is still going to be the same across this. We're going to have the same voltage. All right, and that current is going to rejoin and get read by that ammeter, and Bob's your uncle. So let us do the two questions and we will be done with the electric circuits for this question paper. All right, question 9.2.2 says when switch S1 is closed. So switch S1 is closed, right? And what happens? And switch S2 is open. Switch S2 is still open. The maximum current through the circuit is 3.6 amps. Calculate the root mean square current in the circuit. All right, so we have an AC current that is moving through the circuit in a repeated fashion, in a waveform fashion, right? So essentially, when it says the maximum, it means this peak. At the peak there, so the maximum current is going to be equal to 3.6 amps. But the root mean square is the value that is going to be the same as the DC. So DC does not do this wave, and it won't be using the peak value. So the RMS value will probably be somewhere there, and it's going to be constant, right? So yeah. So with the RMS value, IRMS is actually equal to the square root of 2 multiplied to the maximum current in this case. So what we're going to do is just substitute what we have for our max current, and that is 3.6 amps, and we will find that our IRMS, so our RMS current, the same current that is going to be read by a DC current, is going to equal 2.55 amps, and that is the question. All right, so question 9.2.3 says when switch S1 is open and switch S2 is closed, the root mean square current in the circuit is now 2.62 amps. All right, so S1 is open and then S2 is closed. All right, so that means the current that we have is not going through the kettle, but is going through the toaster. So that's going to be all the current, and we are told that that current is the root mean square. So it's the same current that's going to be read by a DC current. All right, cool. So the question asks us to calculate the energy consumed by the toaster in 2 minutes. We're essentially meant to find the power consumption of the toaster in 2 minutes, and you can use this to even map to how much it'll be in terms of your electric bill, how much it will cost in actual rands. So let us write down all the information. So we have an IRMS equals to 2.62 amps, And then we know that our power is equal to our voltage multiplied to our current, right? In this case, it has to be IRMS, right, as well as VRMS. Okay, so we are told that our VRMS is 220 volts, and that is multiplied to 2.62 amps, and our power in watts will give us a value of 576.4 watts, right? But we're asked to find the power consumption in 2 minutes, or the energy used in 2 minutes. So the energy consumed by the toaster is equal to the power multiplied by the time, and the time has to be in seconds, so 2 minutes multiplied by 60 seconds, that gives us 120 seconds. Alright, so our power, we're just substituting now. Our power, we found that it's equal to 576.4 watts, and that is multiplied to 120 seconds. And you'll see that the answer that we have is 69168 watts per, well, yeah, is it per second? No, it is not watts per second, but rather watts seconds, and that is actually the unit measure of joules, and that is going to give us a final answer of 69168 joules.